Okay, we're recording. So picking up where we left off last time. So we were talking about rewriting double integrals as iterated integrals. And, how does that slicing process look and how do you find the bounds? It's really the hardest part in most cases. When the domain is not a rectangle. Okay, so for this example here, I'm going to take the same double integral and I'm going to show you how to turn it into an iterated integral in two different ways. Because, of course, we have two different ways that we can do the differentials, right? You get dy dx or dx dy. Either one's fine in some sense. Okay, so let's play it out and see what happens. So starting with this up on top here, we're going to do our x slicing first. And, of course, as you go perpendicular to the x-axis, your slices look like this. Okay, so that said, where are first and last? The first slice is there at that point. How are we going to figure out where that point is? Now, notice that that point wasn't actually given, right? It's not like I, in the statement of the question, have specifically indicated that that point is certain coordinates. What we can see, though, is this is the intersection of that curve, which has that equation, and that curve, which has that equation. Right? And so if you want to know where this point is, or specifically if you want to know that x-coordinate of where that point is, because that's what we're interested in the lower bound for x, then you need to solve for x in this pair of equations. Right? And a little bit of algebra will let you know that the answer there is, well, that's actually, there's a little twist that happens, isn't there? You do this algebra to solve for x, you get algebraically, you get two answers. You get 2 and you get minus 2. And here's where the picture kicks in. You have to look at the picture and from the picture make the appropriate inferences and decide whether you should choose the plus or the minus. And in this case, it's very clear that what we're looking for is the lower of the 2 bounds, and so obviously I'm going to choose the minus. Okay. All right. So that's where I get that minus 2 from. Very similar analysis for the other point. For the upper bound. For the upper bound, I am looking for this point, which is on that curve and that curve, which are this, and you quickly notice it's the exact same 2 curves, and so the exact same algebra gives you also the upper bound. And of course, now again, algebraically, you're going to find 2 options, and the picture, right, will be your guide in helping you make the right choice for which one is actually the upper bound in this case. Okay. All right, so let's see. Let's talk about the inside bounds now. How do we get to the inside bounds? We're going to fix an arbitrary value of x. We're going to focus our attention on that x slice. In particular, then, we're going to think about y moving along from y1 to y2, which I like to visualize as being on the slice. Okay. So that said, okay, lower bound. Well, there's the lower bound. It comes from this point, which is on that curve, which has that equation. Now, here's where some students will make a mistake, and so in some cases, and so I like to emphasize, once you've identified the correct equation or equations, make sure to remind yourself what you're actually looking for. We are looking for a value of y. Here, we're looking for a y bound. In particular, we're looking for the lower y bound. And if you want to find a y bound, then you need to solve for y in the equation in question. And solving for y in this equation gives you x squared. Notice y is a function of x. Said differently, the inside bounds are functions of the outside variable. Cool? All right. Likewise for the upper bounds. I'm going to let y'all think that one through on your own. It's very similar. Okay, now that gives us an option. So here's an iterated integral. You can plug and chug with that. Just for fun, though, let's do it the other way. Let's switch the differentials and slice it up that way and see what happens. The outer bounds are pretty straightforward. Y goes from there to there. The first y slice is there, which is kind of obviously 0. The last y slice is, well, it's here, which I'm going to think of as that point, but it's y equals 4. That's the equation of the line in the first place, so pretty clear what that upper bound is. Okay, and per the process that we go through, we now fix a value of y. We think about x ranging from lower bound to upper bound as sort of moving along that y slice, where just for emphasis, again, y is now fixed. And for that value of y, x starts at that value, which comes from that point, which is on that curve, which has that equation. Again, make sure to note the connection. Bound relates to a point, which is on a curve, which has an equation. And again, pause to remind yourself, this is where a lot of students really do get a wrong answer. So many students will look at this and say, oh, the equation is, like x squared or something, and then they will put an x squared there. You can see the temptation, right? Because, well, that's the equation for the curve that the bound is on, and I don't know, it kind of looks right. This is why I like to pause right at this point and say, look, remind yourself what you're looking for. You are looking for a value of x. We're looking for the lower bound as x ranges. As we move along this y slice, x is what is moving. We're looking for an x value, and so we need in here to solve for x. And so within that equation, we need to solve for x. And when you solve for x in that equation, note a little bit of work is required there, not a lot, but a little bit of algebra is required to solve for x. You get, well, again, we have this kind of choice. Wait a minute, are we looking for a lower bound or an upper bound? In this case, we're looking for the lower bound, so I guess I want the negative one because we're looking for the lower bound. And so minus square root of y is that lower bound. It's got nothing to do with x squared. Does everybody follow? Everybody happy? Okay. All right. This kind of thing is not rare. This kind of circumstance where you can look at the equation and you can't just kind of just eyeball, have a kind of a feel, okay, I'm just going to take this part of it and kind of stick it on there, right? And that's what they teach in a lot of high school multivariable calculus classes. And it's really not okay. Not only will it give you wrong answers, it is not persuasive. Right? It is not a legitimate argument. So make sure to be careful and think it through. Likewise for the upper bound. Okay, now let's look at one thing about this circumstance we find ourselves in. We were interested in a double integral. We've turned this into an iterated integral, but when we were deciding which way to slice, it wouldn't immediately be clear which one of these orders of the differentials would be the one that would lead to the better choice. For whatever it's worth, I like this result here quite a bit better. This one I'm scared of. Let me explain why I'm scared of this one down here. It's tempting to say, oh, it's just bounds. You just plug in for the bounds, whatever, right? Here's why I'm scared. This inside integral here, what I have circled in purple, this inside integral that's going to have square roots plugged into it, is my integrand for my outside dy integral, right? And so depending on how bad this antiderivative of little f is, once you plug in some square roots into it, that might be a really ugly dy integral on the outside that you'll be staring down the barrel of, right? And so this is highly undesirable. Everybody happy? Okay. Next natural question. If one is clearly inferior to the other, how do I decide? How do I make this choice without writing them both down? Right? How can I anticipate? How can I make a good choice of ordering the differentials in advance? And I have an answer to this question. Now, this is not perfect, and there are exceptions to these kinds of rules, but I find that in a great majority of circumstances, this leads you in the right direction, and it goes like this. Ultimately, deep down, where did that square root come from? It came from the fact that I had to solve for x. Why did I have to solve for x? Well, because I put x on the inside. So here's what I advise. Look at the ugliest equation that you're dealing with, right? Ask yourself, which variable would I prefer to solve for? And again, strong preference. I have a strong preference. I would like to solve for y. Much better, right? So whichever variable you want to solve for, put that on the inside. That's my rule. Because by putting it on the inside, I'm pretty much guaranteeing I'm going to have to solve for it, not the other one, and thus good news and not bad news. Everybody happy? Yeah.
So for like rectangular functions, when it says like when x or treating x as constant or y as constant to differentiate between the two, what is kind of like the phrasing for these scenarios?
So you mean like a rectangular domain?
Yeah.
With a rectangular domain, the shape of the domain is not going to make much of a difference either way. Kind of, do it either order you like. The only thing that might matter with a rectangular domain is the integrand itself might be harder or easier to do a couple of anti-differentiations depending on which order you go in, and that's just, that's hard to anticipate. Go ahead.
So if you were asking us to do like one in specific, like with respect to y or x first, how would you phrase that?
Like if I were making the selection for you,
yes.
Like if I were saying I wanted you to do this one and not that one,
yes.
I would probably just explicitly write it out and explicitly indicate. Or conceivably, let's see, what would I do? It's really hard for me to anticipate test questions, right? So I don't know how I might phrase it, but the main thing that occurs to me now would be I would just explicitly write it down. Yeah. Is that cool? Okay. All right. One other quick thing, a little bit of language. The curves, here we have a parabola, right? And then here we have a line. And you see the domain D is described as being bounded by those curves. And we've been operating on the assumption that it was that region which is bounded by those curves, right? Seems reasonable. I just want to point out there's two things that make this the right region that is bounded by those curves. One is, obviously, the boundary of this region consists of those curves. The thing is, I could say the same about this region up here. Right, that region there, the boundary of that region consists of, the green curve and the blue curve. So how did I know that I meant this one and not that one? And the reason why is that this term bounded by also means bounded. And bounded means it does not extend infinitely in any direction. It means that you can draw a circle around it. You can put it in a box, right? And so it should always be the case that whatever algebra I give you, if I say bounded by, the question should, that phrasing should be used only if that language indicates a unique region of the plane. Okay. But you do have to make the right selection, and I always think through my phrasing of these kinds of things as carefully as I can, and so anyway, it's on you to interpret correctly. Okay, another example that demonstrates a motivation for how you choose which order to slice. Now I'm going to start moving a little faster because we've done a bunch of examples at this point of slicing up regions, right? So, and we're going to do more over the next several weeks. Here you go. You got a triangle given. Let's do dx dy. Let's see what happens. not hard to persuade yourself that y goes from 0 to 1. And then for any given value of y, if I look at the range of values of x, x will go, well, kind of from that point to that point. And I'm going to let you all think through the details, and those points indicate these bounds for x. Okay. All right, make sure you can fill in those blanks. Now let's do it the other way. Tempting to say, well, we'll start with x going from 0 to 2. I mean, it does. But if you say x goes from 0 to 2, here's the problem. For some of those values of x, this is what determines the upper bound for y. But for other of these values of x, this is the curve that determines the upper bound for y. They're different curves. They have different equations. They will give different expressions for your upper y bound. And you can't do that. Right? So that's why you have to do what I have written out here. You have to break this up into two separate x ranges. X first goes from 0 to 1. X subsequently goes from 1 to 2. And having broken it up into two pieces like this, I can now address the y bounds, no problem, on each one of these iterated integrals that I'm developing. What's the range of values of y for the first one? Well, the upper bound for y is going to be from a point on that curve, which has an equation, blah, 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 and you can find that upper bound for y. And then, now totally separately, for the second x integral, the range of values of y, the upper bound will be from a point on this curve. Totally different equation, totally different than upper bound, and details for you all to check out, and that will be your upper bound for y for the second chunk. So you have to break it up into two separate chunks. Everybody okay? Yeah.
Why is it 2 minus y on the one, the integral above it?
Yeah, so just real quick, this right there is that is the x coordinate of this point being on that curve. You write down the equation of this curve and then solve for x, and what you get is 2 minus y.
Wouldn't the equation for that line be y equals 2 minus x?
Yes. And we're looking for an x, so you got to solve for x. So that's that same landmine. You got to always make sure that you solve for the variable that you're finding a bound on. Yeah. Is that cool?
Yeah.
Okay. Cool. All right. So look, again, we find ourselves in this circumstance where we've seen a couple of different options of how to break down this integral. One's obviously better than the other. Right? And I suppose we could write them both down and then choose, but wouldn't it be nice to be able to anticipate? So here's my observation. The way that I would choose between these is to recognize that in this latter case, what went wrong is, as I was slicing, in the process of slicing, I sliced through a corner. That's the way I like to say this, because it's geometrically very evident when you slice through a corner. I mean, there it is. It's all sharp and pointy and stuff, right? So when you slice through a corner, the point is that is what happens geometrically when one curve intersects with another curve, right? And the fact that my upper bound for y jumped from one curve to the other curve is why I had to switch integrals. And how does a point continuously moving point jump from one curve to another curve? Well, only where the curves intersect, and when curves intersect, they typically make corners. So it's a nice, simple little rule of thumb. Try not to slice through corners. Let's see here. Let me sort of walk you through how you would put this into practice. You would say, okay, if I do my y slicing first, then I start slicing through a couple of corners, but hey, no problem. I was going to start a new integral anyway, so that's not an issue. Nothing. I end at a corner, Again, no problem. I was done already anyway. So I didn't slice through any corners there in that slicing process. Whereas, on the other hand, doing my X slicing first, I start at a corner, again, no issue, but as I proceed along, I slice through a corner right in the big middle of my range of values of X. That's why I have to stop and start a whole new integral as I proceed. So, nice little simple, pithy little rule. Try not to slice through corners. Everybody good? Yes.
Why is it not an issue slicing through a corner on like the inner function? Like for the first one. Like for
well,
dx.
yeah, it would be, but I feel like we didn't.
Okay.
Right. So let's look at. So you feel like on the green one here?
Yeah.
Yeah.
Like for y and then 2 minus y.
Yeah. So this x bound from y to 2 minus y, I'm going from there to there. Neither one of those is on a corner.
Okay.
Right. That's right in the middle of a nice smooth line. So is this one.
Okay.
Yeah. Okay. Okay, so we have a couple of nice little rules. Think about what you want to solve for and slice accordingly. And try not to slice through corners if you can avoid it. Okay. All right, here's another little issue that you may have to worry about sometimes. Sometimes the domain is just not given. Easy example here, I have a couple of surfaces. This one and this one is some sort of a plane, whatever, not to scale. I'm looking for the solid that's between those two surfaces. There's, of course, only one finite amount of volume in between those two surfaces. That's kind of right there, but I like to look at it separately over here. Okay, cool. So far, everybody happy? You'll notice, of course, now what I can do here is I can slice up my domain down here, whatever that is. I can slice it up into little pieces. On each little piece down here like this, I can talk about how much volume there is sitting above that piece. Right, and again, French fries and all that. The total volume is the sum of the volume of the French fries, and that gives us this right here. All good so far. Now here's the tricky part. Again, what's my domain? Right, I have a kind of an approximate picture of it. It's the shadow, if you will, of this solid, but what is that, and how do I get my hands on it? Okay. So, okay. You got to be careful with this. Some students will do the following. Some students will say, look, I'm looking for where this surface intersects with that surface, because that intersection, right, if you look at its shadow, right, the intersection will give you sort of the boundary of your domain, and that part's all good. It is true that the boundary of my domain is going to come from where these two surfaces intersect. Sure. And then students will do the following. Students will say, all right, well, I guess, therefore, I want to set this equal to that. And that doesn't make any sense at all. There is no such thing as setting two equations equal to each other. It's just not a thing. It doesn't make any sense. Right? It's total garbage. I'll point out if you think that maybe there might be some meaning to this. Why did I pick the left side of this equation instead of the right? Why didn't I just say x squared plus y squared equals 7? That'd definitely be different, right? So why didn't I do that? Why didn't I just say z equals 7? Right? And it's because, again, deep down, ultimately, the point is none of this up here makes any sense at all. Right? So please, please, please don't make that mistake. I see that so often. It's just not a reasonable thing to do. Now, let me show you what you should do in this circumstance instead. Let's see here, cleaning up my mess. Again, what I'm looking for is points that are on the boundary. Now, let me observe any point in the domain there is a value of z that gets me up to the bottom surface, and there is a value of z that gets me up to the top surface. All right? Now I'm going to make the case now that what I'm looking for, these purple points on the boundary I'm interested in, those are the points where going up to the top surface, going up to the bottom surface and going up to the top surface, same amount. Right? So the big idea, how I'm going to find these purple points, those purple points come from where z1 is equal to z2. And that is something that you can specifically do in the equations. There's z1 and there's z2. So set those equal to each other. Now, a little bit of legwork necessary, right? I don't have this z on the right here. I don't have that solved for you. So you're going to have to do a little bit of algebra and actually solve for that z. And when you do that, let's see here if I can. Okay, there we go. You solve for those z's and set them equal to each other, and you get this right here. And that's an equation that represents that boundary. Is everybody on board? Okay. While we're here, I will make the observation that, let's see if I can, if it will let me pinch. It makes me do it several times before it actually works. I don't know why. This equation is the equation of a circle. And how you make that, how you sort of make that connection, how you get this sort of non-standard form thing into an explicit form equation of a circle requires completing the square. Right? So make sure to remember how to complete the square. Again, this is something that's underappreciated in high school algebra classes, and it comes up. It really does, and it's, I think, an important bit of algebra that very often students, come to a class like this maybe not having seen before or not having done much of. Yeah.
So if you were to carry on with this problem and actually executing it, would you f of x that you'd be evaluating within the dA, that would just be those two expressions explicitly subtracted from each other?
Yep. Just like I had. Yep, totally. Is that cool?
Yeah.
Right.
And then what we just found is the bounds for width.
Well, what we just found was the equation. So there's still work to be done to figure out what the bounds are. Right? I just found the equation of that curve, and then what you'd have to do is take this curve and slice it up in the usual way. Dx, dy, dy, dx, take your pick. And this equation is what sort of guides that process. Yeah. Okay, so moving along. Section 5.3 is a weird section. Section 5.3, I think, should be an example in Section 5.2. There's not that much happening here. I'm going to just kind of walk you through the example pretty much. And this comes up sometimes, maybe not a tremendous amount, but it is a very creative and clever approach to solving a problem, and so I think it's worth talking about. So, for example, what if we found ourselves looking at this iterated integral? We want to compute this iterated integral. Well, you could just have at it, I suppose. That said, another option, another thing you could do, you could reverse engineer and find what is the original domain that this iterated integral came from. Now, why would you want to do such a thing? Reasonable question, but I'm just going to point out a domain for a double integral gives an iterated integral, and so you could just kind of think backwards and reinvent what the domain was. Okay, having done that, you can then slice up that domain in the other order. Now notice here, the original integral was dx dy. Now I have now chosen to slice up my domain in the opposite order, dy dx. Right? Okay. That gives me then a different iterated integral, right? I started as being asked to compute this iterated integral. Now I'm looking at this different iterated integral. Why would I ever want to do such a thing? And here's why. If you look at, there we go. If you look at this iterated integral and you look on the inside is an integral of e to the x squared dx, and you can't write that down what they call enclosed form. You can't write it down reasonably, in other words, without using power series. So just logistically, we're kind of dead in the water on this one. Everybody see the problem? This is pretty undesirable. So it's pretty neat then to be able to say, all right, well, look, yeah, slicing dx dy, that was sort of a dead end. So let's do the dy dx. And now we look at the inside integral. It remains at a glance kind of scary because you still have integral e to the x squared. It looks bad, but it's dy. That means that x, being the outside variable, is a constant. That means e to the x squared is just a great big scary looking constant. And the integral of a constant is that constant times y. In this case, you plug in the bounds, and this is what your inside integral turns into. It turns into no problem, basically. Totally doable. And then that integral, the outside integral, you can totally get just with a u equals x squared substitution. That makes sense to everybody? That's clever. It comes up here and there. Point is, it's clever. And that's really all there is to say about section 5.3. Okay. All right. Okay, so moving along, 5.4. Y'all can probably predict where a lot of this is going to go. We're going to talk about something called triple integrals. It's a lot like double integrals, just a little bit more so, right? So what was the purpose of a double integral? A double integral was originally, the very first thing we wrote down for a double integral was, look, I just kind of want to make a Riemann sum kind of thing with some hopeful optimism, because sometimes stuff might accumulate over an area. And a double integral is just a way of kind of dealing with that algebraically. Just, okay, all right, well, we'll just look at every little piece across an area and kind of add those up. Triple integral, same thing. We can expect sometimes to have quantities accumulate over a volume. Chop it up, add it up over a volume. Now, what is this quantity that I'm talking about? Very importantly, I don't want to say. I don't want to pigeonhole myself, right? I want the ideas that I'm about to go through be applicable very broadly. But there's lots of quantities that accumulate over solids, right? And the easiest example being mass, right? If I have a big chunk of stuff, of mass, and if I chop it into little bitty pieces, the whole is the sum of the parts. That's what accumulation is, right? So mass accumulates if it's distributed over a volume. Populations accumulate over volumes, right? If I have let's say this is an aquarium, right? And I've got a bunch of, let's say bacteria floating around inside of the fish tank, right? But there's more bacteria per unit volume down low and less up high. Well, total number of bacteria is the sum of the numbers inside each little box. It accumulates. Likewise, and recall we need this in order to be able to have a Riemann sum address our problem at hand. I need to know that whatever I'm looking for on any individual little piece, I need to know that the answer to the question on that piece will take this form. I need to know that it'll be something to be determined times volume. Right? That's gonna be necessary if I'm gonna relate things to pieces of volume. I need to talk about quantity in question per size of volume. All right. So, any question that fits that form, accumulating quantity that I can think of as being related in quantity to volume. If you're looking at a quantity of that sort, then this 3 index Riemann sum will answer your question. And again, this is worthy of a name and a notation. The name is triple integral. The notation is exactly what you would expect. The only sort of tricky curve, I suppose, on this is you do have to kind of think through, well, wait a second, what should we call delta x, delta y, delta z? Well, its job is to represent the volume of one of these little sub-boxes. And a little piece of volume we abbreviate as dV. How are we doing? All right. Okay, so let's see one. Real quick, as before with double integrals, the book is a little bit of a higher cut than Math219 takes. And good for them, right? The book is nicely rigorous in wonderful ways that have value in different contexts. For our class, we're not going to make any discussion of irregular partitions or non-standard test points. So ignore all that stuff. Okay, so example then. Suppose I want to compute the amount of mass in a region, total amount of mass in a region. And notice our two conditions are satisfied. Mass is an accumulating quantity. Total mass is the sum of a bunch of little pieces of mass. The whole is the sum of the parts. That's just how mass works, right? Secondly, on any little piece, I can talk about how the amount of mass in that little piece relates to the volume. And in fact, this is a very common sort of means of talking about how mass is distributed. We talk about density as being mass per unit volume. And of course, mass per unit volume is the thing you multiply by volume to get mass. So that works as well. And sure enough, we've ended up with a triple integral, and now we just have to figure out how to compute triple integrals. Is everybody with me? Okay. See how it's just like double integrals, but kind of three-dimensional? Okay. All right. Okay, now a bit of a warning. I'm going to rewind a little bit here, and let's talk for a second about single variable integrals. And I know y'all know how to do single variable integrals. Most people's favorite way to visualize single variable integrals in a Calc 1 class is area under a graph. Yeah. Okay, fine, whatever. Y'all have heard me pitch a few times this idea that, it also can be thought of as an accumulation of stuff, whatever the quantity is, some sort of an accumulation that happens over an interval from A to B. And we just need to know what is the stuff per unit length along the interval so that on any given little piece we can make sense out of it. So you got two options in some sense for how to think about single variable integrals. Likewise, a couple of different ways to think about double integrals. A lot of people like to think of it as volume under a surface graph. But of course, you could view it as an accumulation of stuff over a two-dimensional region. Any sort of stuff. Okay. All right, now let me try to persuade you why I am kind of cool on this point of view over here. And the reason why is to think about, all right, well, what happens when we move on to thinking about triple integrals and why, there we go. Okay. What happens if I want to think about a triple integral? How would I visualize a triple integral? Well, for a single variable integral, I get a two-dimensional picture. For a double integral, I get a three-dimensional picture. And you notice the pattern. To make sense out of a triple integral in this sort of analogous way, you would need a four-dimensional picture. And that's not on the table. It's not possible. You just can't do it. Right? Does that make sense? So, yet another reason why. I mean, you should be, let's say, cautious about thinking about integrals from the point of view of graphs. Graphs just aren't accessible. In a lot of routine circumstances, perfectly. This is a three-dimensional question here. A triple integral involving, stuff accumulating over a solid. Like every stuff that we experience in regular everyday life, three-dimensional, right? no way to visualize it from the point of view of graphs. So this is why this is one of the reasons why I push this alternative point of view on integrals. And I recognize that in single variable calculus this isn't really worth worrying about. But I encourage you to think of integrals as representing accumulations of stuff over whatever domain is indicated, right? So here we have a domain that's a two-dimensional region. And here I have a domain that is an interval from A to B, one-dimensional region. So with this point of view, what's a triple integral? Hey, no problem. A triple integral just represents stuff accumulating over a three-dimensional region. Nice and simple. No creepy four-dimensional sci-fi imagination required. Everybody good? Okay. All right. So I know that this requires kind of reorienting things around in your mind, and you may be really heavily attached to this, especially for single variable. I think it's worth taking some time to try to sort of get accustomed to thinking about it this way instead. Okay, enough of that. All right. Problem. We've got this diagram. Y'all remember this diagram? There was an analogous version of this for double integrals, right? And we made various arguments and connected this and that and drew conclusions from the connections, et cetera, et cetera. What we just got through talking about is that there is nothing to put here. Four-dimensional volume under a graph? It's not a thing I can make sense of. Furthermore, then, I can't make these connections like I did with double integrals. So it's all well and good that I can take my pen just died again, man. Sorry. I just charged the thing. I don't know why it's run out of juice on me. Oh, man. There we go. This gives y'all a break for a second here. Okay. There we go. Okay, so all well and good that various applications, I can think of these quantities as accumulating over three-dimensional solids and write them as a triple integral. Fine. And of course, once I get it down to an iterated integral, then it's just a matter of sort of plug and chug. But how am I going to make this connection like I did in the previous context? How am I going to make the connection between triple integrals and iterated integrals? And the answer is I'm going to ask you to trust me because while there is no geometric argument that I can make like I did with double integrals, there is a perfectly acceptable algebraic argument that you can make, and it's just that algebraic argument has some delicacies to it, and I don't think it's worth writing that down. But anyway, I'm just going to assert that as we would expect from the pattern, in fact, yes, it's perfectly reasonable to write a triple integral as a triple iterated integral. And that's what this theorem says right here, that you can always rewrite a triple integral as any of several different options of iterated integrals. Y'all will buy that? All right. Oh, and as previously, please make sure not to make any nonsensical arguments, such as just instantly writing down mass as an iterated integral. It doesn't make any sense. That doesn't hold any water. And again, all you have to do is just write down the triple integral first, and then you have your iterated integral. It's just that one extra little thing to write down that turns nonsense into perfectly reasonable with, again, like 5 seconds effort. Make sure to do that. Okay. All right, let's crank one out. Now we'll talk about how to slice and how to figure out your bounds later, but I just want to get a win under our belt concerning computation. How are we going to compute the mass? Let me clean this up here. How am I going to compute the amount of amount of mass in a rectangular box? Mass distributed according to that density function. Step 1. Whole is the sum of the parts. Mass is an accumulating quantity. Just like we discussed above, that makes it a triple integral of density. So that's step 1. Step 2, triple integrals are iterated integrals. Now let's think through real carefully here, though, before we move on. Where do these bounds come from? Notice the order that I've got my differentials here, and keep in mind bounds correspond to differentials in a outside-in sort of grouping, sort of outside pairs with outside, second pairs with second, inside pairs with inside. Right. So let's ask real quick. Then what's my range of values for y? Well, you can see right here in the rectangular description that I have here. This was the x bounds. This is the y bounds, and this is the z bounds. So my y bounds tell me the bounds for my y integral. Likewise, let's see here. What are my x bounds? Well, here you go, 1 to 2. And then lastly, what are my z bounds? Well, there's the z bounds, 0 to 1. Everybody happy? All right. Okay, so application to triple integral to iterated integral, and then step 3 is the sort of the plug and chug. I'm in the wrong mode here. Plug and chug, and there's a lot of chugging to do there, but that's a lot like it is for double integrals. Just be careful. Yes.
Is there a reason behind switching the order from like x, y, z to z, x, y?
They're all, in this case, especially with rectangular bounds and with this integrand being pretty boring, it really just doesn't matter much. It's kind of take your pick. I had 6 different options. I did something other than alphabetical order just to show that I can. All right, I don't want students to get too accustomed to something arbitrary that isn't a good way to decide. Right? Is everybody happy? Do be aware. Reminder: there is a sticky point, easy to mess up. A lot of students will look at this z integral here, right, and think, okay, well, how do I do the antiderivative? And they see, well, gosh, I've got an x and a y and a z, and what's a function of what? Or how do I deal with this multiple variables business? And just remember, just like with double integrals, variables that are further to the outside are constants. And constants just come along for the ride, right? Nothing happens to the constants. So really, in taking this first antiderivative, I've just got constant times 2z. And the z antiderivative of 2z is z squared. All right, so always heads up, you always got to pay attention and be actively thinking about, wait a minute, which variable is playing what role in this situation. Okay. All right. How do you turn a triple integral into a triple iterated integral? How did we do it for double integrals? Well, I cheated, right? I drew a picture of the graph. It was a nice visual convenience, and I can't do that here. There is no picture of the graph of a function of 3 variables because if I run out of space, there's just not enough dimensions. So what I'm going to again ask for your trust is I'm going to just claim the process continues to be analogous, and I claim this is what we do when we are doing this for double integrals. One variable at a time, we slice, we identify the bounds, then we fix a slice and move on to the next variable that we slice. All right. So let's walk through that process. Arbitrarily, I'm going to start in the x direction here. Here's my x-axis. Here's what it looks like to slice perpendicular to the x-axis. Those slices look kind of like this. All right? Everybody happy? That's what it looks like when you slice up this lump perpendicular to the x-axis. Okay, so now that's what the slices look like. Let's think about what the bounds are. The very first value of x corresponds to, well, where is that very first slice? I mean, as I'm slicing perpendicular to the x-axis here, there's going to be sort of a first one, which given the sort of roundish shape of this thing, there will be sort of a point on the back side there. That's where there's the smallest value of x. And then, of course, the upper bound for x is going to come from that last slice, which will be a point kind of on the front side. Is that cool? All right. All right. So then we let's see here. As it says here, we're going to fix a slice. So we're going to consider now only this slice for the moment. And as the instructions over here say, we're now going to go up. We're going to start the whole process over again. This time, though, with respect to y. No particular reason we could do z, but I had to make a choice here, and arbitrarily I'm going to do y. All right, so what do slices look like? All right, well, here's a value of y. A slice perpendicular to the y-axis would be something like that. So now you got to keep in mind, though, we've already got an x. We've already got an x slice. Our x slice is already a little two-dimensional thing, right? We're now taking y slices, not of the original solid. We're taking y slices of our x slice. And how these slices intersect. These slices intersect in a, the slices intersect in a little line segment there. Everybody see that? Y slice of an X slice will just be that little line segment. And again, we got to play first and last games. Now, my picture is getting increasingly muddy, so let me kind of clean up the picture here. Let's see, looking at our shaded gray X slice, the very first value of y is going to be the value of y that corresponds to that sort of first, if you will, right? The very first one of these y slices will be some point over here on the left side of my X slice. My last value of y will be the coordinate, y coordinate of, well, whatever is this point over here on the far right of my X slice. Does that all make sense? Yes?
What is the big oval that the small gray one?
Yeah, so the great big sort of lump is my original solid, right? But I've already done my X slicing. I've already recognized X is going to have to go from X1 to X2, right? And by the way, we'll see details and examples, eventually, not today, of course. So once you know what the range of values is for X, you have to fix an X slice, and then for the remainder of your slicing, look only at that X slice.
Can you choose the X values, or what they give?
Know that it's not given, but it's determined by whatever the solid is, right? So the X1 and the X2, X1 comes from what is the furthest back, if you will, the sort of the point on your solid that's furthest into the page, right? And then the X2 comes from whatever point is the furthest out of the page. Yeah. Yes.
Is it fair to say that we're decreasing the dimension with every step, it goes from a 3D shape to a 2D?
Yes, that's absolutely right. Yeah, for sure. Yeah. Okay, so y1 and y2, right? We have a lower bound for y, upper bound for y, and as it says here, once you've determined those lower and upper bounds, we now again fix a slice, right? So now I'm going to take x as being fixed. Now also y is fixed. That means we're looking only at this little line segment, this y slice of that x slice. And now we move on again now to the third variable. And this is really where things become just a little different from double integrals. There's a third variable for which we have to go through the same process. And it's exactly what you would think. There is a lower bound for z that comes from the point on this slice of a slice that has the lowest z coordinate. You have to figure out where that lowest point is and solve for z. And then there's going to be an upper bound for z that's going to come from the point on this slice of a slice with the greatest z coordinate. And again, it's just a matter of finding where that point is and solving for z. And we will fill in details next time. Y'all have a great fall break, and see you on Wednesday. And as usual, if you came in after I did attendance, make sure I mark you present.